A server running Linux is often viewed as the quiet room of enterprise infrastructure, stable, minimal, and largely invisible to the chaos that frequently affects Windows endpoints. That assumption is exactly what makes it attractive to attackers. When ransomware operators want maximum leverage with minimal resistance, they often target areas where security expectations are lower. And Linux, despite its strong security reputation, is increasingly becoming a ransomware target. The uncomfortable reality is that this isn't because Linux is weak. It's because Linux powers critical infrastructure. Welcome to BlueHat Cybersec Academy. This breakdown explores what Linux ransomware looks like in practice, why it was historically rare but is now growing rapidly, how attackers turn Linux environments into high-value targets, and what realistic defenses look like beyond generic cybersecurity advice. A common misconception is that Linux was ignored because it was secure. In reality, it was considered less profitable. Windows dominated desktops and enterprise file systems, so malware authors optimized for the largest and easiest targets. Linux environments were different. They were less common, often managed by experienced administrators, and far less standardized, making large-scale attacks harder to automate. The key point is that Linux was never immune. It simply offered a lower return on effort. That has changed. Today, Linux powers cloud platforms, web infrastructure, container ecosystems like Docker and Kubernetes, databases, and backup systems. In other words, Linux now sits directly beneath some of the most valuable enterprise assets. Attackers noticed. Linux ransomware is not a separate or exotic malware category. Most variants are Linux-specific builds of existing ransomware families, compiled as ELF binaries and designed for server environments, rather than consumer devices. Groups like Lockbit, Clop, and RansomXX have all deployed Linux-capable ransomware in real-world operations. These are mature, enterprise-focused tools built for one purpose: leverage. Another important distinction is that Linux ransomware rarely arrives through casual browsing or random downloads. It typically follows an earlier compromise through stolen credentials, exposed VPNs or SSH services, vulnerable APIs, cloud identity abuse, or compromised container environments. At that stage, the threat is no longer about user behavior. It becomes an infrastructure problem. The growth of Linux ransomware is driven by several structural changes. First, cloud adoption has concentrated critical workloads on Linux platforms, and attackers naturally follow valuable data. Second, identity compromise has become a primary entry method. Stolen credentials, session tokens, and abused IAM roles often provide direct access to critical Linux infrastructure. Third, Linux systems frequently host backup repositories, snapshots, and virtual machine images. Encrypting them can make recovery impractical. Fourth, containerized environments increase potential impact. In Kubernetes environments, a compromised control plane can enable rapid and sometimes automated lateral movement. Most Linux ransomware attacks follow a fairly consistent pattern. The first stage is initial access through stolen SSH credentials, exposed services, compromised CI/CD pipelines, or cloud identity abuse. In many cases, valid credentials are more effective than exploits. Next comes privilege escalation. Attackers seek root access, cluster-level permissions, and visibility into storage resources and sensitive mounts. They then perform reconnaissance, identifying databases, backup repositories, storage volumes, and critical directories. Contrary to popular belief, ransomware does not always encrypt everything. Attackers often focus on business-critical data, while keeping systems partially operational to maximize pressure. A functioning environment with inaccessible data is often more valuable to attackers than a completely destroyed system. Finally, ransom notes are deployed, payment instructions are delivered through Tor-based infrastructure, and communication channels are established. The message is simple: your systems still work, but your data is no longer under your control. Detecting ransomware on Linux can be particularly challenging. Compared to Windows environments, Linux deployments often have fewer standardized endpoint security controls. They rely heavily on custom tooling, headless servers, and operational automation. A deeper challenge is that legitimate administrative activity can closely resemble ransomware behavior. Bulk file operations, tar archiving, rsync synchronization, and automated cron jobs are normal administrative tasks, but they can also resemble mass encryption activity. As a result, detection depends less on signatures and more on context and behavioral analysis. Malicious activity often blends into normal operational noise. Several misconceptions continue to increase organizational risk. First, Linux is not automatically secure. While the kernel may be hardened, most breaches stem from misconfigurations rather than kernel vulnerabilities. Second, cloud providers do not handle all security responsibilities. They secure infrastructure layers, while customers remain responsible for identities, configurations, and exposed services. Third, ransomware is no longer a Windows-only problem. Modern ransomware targets infrastructure wherever it creates the greatest leverage. Effective defense starts with access control. Enforce SSH key authentication. Disable password-based logins where possible. Require MFA for administrative access, and limit SSH exposure through VPNs or bastion hosts. Next, focus on behavioral monitoring. Detect unusual bulk file modifications, rapid extension changes, encryption-like IUO activity, and abnormal file processing CPU usage. Infrastructure segmentation is equally important. Web servers should not directly access backups. Application tiers should be isolated from storage systems, and administrative networks should remain separated. Backup protection must be treated as a priority. Use immutable storage when possible, maintain offline or air-gapped copies, and regularly test restoration procedures, rather than simply verifying backup completion. Finally, secure cloud and container identities. Restrict privileged containers, enforce Kubernetes RBAC controls, rotate credentials regularly, and apply least privilege principles to service accounts. Modern attackers often succeed not by breaking trust, but by inheriting excessive trust. When all of this is considered together, the reality becomes clear. Linux ransomware is not a paradox. It is an evolution. It succeeds not because Linux is weak, but because modern infrastructure is complex, interconnected, and heavily dependent on credentials and trust relationships. Attackers increasingly exploit operational assumptions rather than operating system vulnerabilities. Here's the key takeaway. Ransomware did not simply move to Linux, it moved to infrastructure itself. That distinction changes everything. Attackers are no longer primarily breaking into systems, they are logging into them. And once that happens, the critical question is no longer whether access is possible. It is whether that access was properly constrained from the start. Now, here's your challenge for this episode. Imagine this scenario. A company runs Kubernetes on Linux servers. Backups are stored on a mounted network volume. SSH access relies solely on strong passwords, with no multi-factor authentication. An attacker steals a single credential. Consider these 3 questions. First, where would you expect the initial lateral movement to occur? Second, which target would likely be encrypted first application data, backups, or container configurations? Third, which single security control would most significantly reduce the impact of the entire attack chain? Drop your answers in the comments. Break the scenario down logically. Think like an attacker, not just a defender. If this breakdown helped you understand Linux ransomware as a genuine infrastructure-level threat, rather than a buzzword, the rest of the Malware Encyclopedia series will take that understanding even further. For more deep logic-driven cybersecurity analysis, stay connected with BlueHat Cybersec Academy. Like, share, and subscribe, and I'll see you in the next analysis.